Hi, I'm Drew Festini, and I want to talk today about two of my favorite things, which are Linux and open source hardware. I'm an open source hardware designer at a PCB manufacturing service in the US called OSSummit. I'm also on the board of directors of the BeagleBoard.org Foundation. You may have heard of the BeagleBone. It's a small open source hardware Linux computer. I'm also on the board of directors of the Open Source Hardware Association, and we have an open source hardware certification program that you can find out more about on our website. And I'm also a RISC-V ambassador. So there's many RISC-V virtual meetups around the world, including Munich and Bay Area. You can find out more of them at risc5.org/local. And coming up in a few days, we have the RISC-V Summit, which is the big annual RISC-V event. There'll be lots of interesting talks about RISC-V, so I recommend checking it out. So I mentioned open source hardware. So that's hardware whose design is made publicly available so that anyone can study, modify, distribute, make, and sell the design or hardware based on that design. So in the context of electronics, we're talking about the documentation would be required is the schematics and the board layout in the editable source files from the CAD software. So not just a PDF or an image file. And ideally, though it's not required, is to use open source software. So for example, KiCad. And this lowers the barriers of entry for people that want to participate in the project. You can use proprietary CAD software though, and it can still be considered open source hardware. So it's not required, but it is best practice to use open source software if you can. Then also the bill of materials or the parts list. Also not a strict requirement, but it's best practice for all the components to be available from distributors in low quantity. And the point of all of this is to lower the barriers of entry to enable collaborative development, which is kind of the theme behind open source hardware. I talked more about open source hardware, including different licensing options, in a talk I gave last year, and you can watch that video online. So RISC-V is an instruction set, or an ISA. This is the interface between the hardware and the software. For example, let's say we have a C++ program. Well, that gets compiled into instructions for a microprocessor to execute. But how does the compiler know what instructions the CPU understands? This is defined by the instruction set architecture. So the ISA is a standard, a set of rules that define the tasks the processor can perform. Proprietary ISAs like x86 from Intel and ARM, which you'd find in your laptop and desktop and most servers, in ARM, which you'd find in most smartphones. These are proprietary instruction sets and they require commercial licensing. However, RISC-V is a free and open instruction set. So this started about 10 years ago by computer architecture researchers at UC Berkeley. The professor that started the project has a great talk called Instruction Sets Want to Be Free that I recommend checking out. Sometimes people ask me, what's the V? So this is actually the Roman numeral 5 because it's the 5th RISC instruction set to come out of Berkeley. And why do I say it's free and open? This is because the specifications for RISC-V are licensed under as a Creative Commons attribution, which is considered an open source license. So what's different about RISC-V? Because there's many instruction sets out there. Well, it's a simple and clean slate design, kind of built upon the many decades of knowledge and skills that the team at Berkeley had developed. It's far smaller than commercial instruction sets and has a clear separation between unprivileged and privileged instruction set. It also avoids baking in microarchitecture or technology-dependent features into the instruction set. So there's a separation there between the standard or the specification and how it's implemented. So also RISC-V is also modular, so it's both extensible and you can specialize it for different use cases. This is because there's a small standard base with multiple standard extensions that makes it suitable for everything from a tiny microcontroller to a big supercomputer. And it's stable, which means that the base and standard extensions are frozen now, so they'll always be supported by a RISC-V processor. And then additions are made via optional extensions. For example, there's a vector processing extension that's being developed right now and a hypervisor extension that's being developed. But these don't require new versions of the base ISA, they're just optional extensions on top of that. So there's 4 base integer ISAs. There's RV32I, which is 32-bit, and it's less than 50 instructions, so relatively easy for people to implement in a design. And then there's RV32E, which is just a reduced register count to make it better for implementing small microcontrollers. And there's RV64I, and this is 64-bit, and this will be the one that we're most interested in terms of RISC-V processors that can run Linux. There's even 128-bit, so this is kind of future-proof to make sure there's enough address space when non-volatile RAM capacities increase, potentially. It also is beneficial for security as well to have a larger address space. So there's RISC-V standard extensions that I mentioned, and those include multiply, or those include M for multiply and divide, A for atomic, FD and Q for different precisions of floating point, and then there's G, which is general purpose. So this is equivalent to several of those existing ones, the integer, multiply, atomic, float, and double float. And then there's C, which is compressed instructions to conserve memory and cache. So this is similar to ARM Thumb. And as I said before, these standard extensions have been ratified, so they will be supported forever as long as the processor conforms to the RISC-V instruction set. And then Linux distros like Debian and Fedora are targeting RV64GC. So if you're looking at processor designs and you're interested in ones that will be supported by Linux distros potentially, then you want to be looking for RV64GC. And here's the base instruction sets along with the standard extensions on a reference card, which is kind of nice to see it all there. And if you were to compare this to something like Intel, you can see that it's much easier to wrap your mind around RISC-V. If you want to learn more about RISC-V, including the different base instruction sets and the standard extensions, and also some new ones that are being worked on like Vector and Hypervisor, check out the RISC-V reader. It's only about 100 pages. I really recommend giving it a quick read through. It's available in several different languages as well. So RISC-V International now controls the specifications that were originally developed at Berkeley, and you can find this at riscv.org. So it's a nonprofit organization with it's always growing. It's probably over 700 members now from 50 different countries, including companies and universities and more. You as an individual can become a member free of cost. It's also free of cost for nonprofits to join as well. And there's also a YouTube channel for RISC-V International that has hundreds of talks from over the years, and that's one of the ways that I've learned a lot about RISC-V, so I highly recommend checking that out. And companies plan to ship billions of devices with RISC-V cores. NVIDIA is actually already shipping RISC-V cores for system management in its GPU products. And Western Digital has announced that they're planning to swap out the controllers in all their different storage devices with RISC-V based designs, which will be a large number of devices out there in the world with RISC-V cores in them. So one of the reasons to choose RISC-V is to avoid instruction set licensing costs and royalty fees. This includes the legal costs, and also I've heard mentioned the long delays. So to license something like an instruction set, it can be kind of complex and it can take a long time. And the researchers at Berkeley mentioned that was one of the reasons why they decided to just go ahead and design their own instruction set. But more importantly than just saving on licensing and royalty fees, it gives you the freedom to choose your own microarchitecture implementation. So the way in which you implement the instruction set is up to you. Whereas with ARM, only a few companies like Apple and Samsung and Qualcomm have architecture licenses that allow them to do their own custom implementations. So everyone else is pretty much just licensing existing cores from ARM. And with RISC-V, you also have the freedom to leverage existing open source implementations. So for the context of Linux, there's Rocket and Boom from Berkeley, and there's also Ariane from the ETH Zurich Pulp team that are capable of running Linux. One of the other things that's really important when it comes to an instruction set is software support, and RISC-V already has a well-supported software ecosystem. If you click on that link there, it'll take you to a GitHub where RISC-V International keeps a list of support for all the different operating systems and languages and toolchains, and it's evolving very well. Kemaraj gave a talk back at the Embedded Linux Conference North America about the state of software development tools for RISC-V. So if you're wondering about like particular language you're interested in or library, definitely check that out and you can find the latest information. But overall, it's pretty well supported. So most of the things that you would expect to be there are there now. So RISC-V International is based in Switzerland. So back at the beginning of this year, previously there had been an organization called RISC-V Foundation that was US based. And back at the beginning of this year, that RISC-V International was incorporated in Switzerland to alleviate any concerns from the membership over US politics. Also, the European Union, India, and Pakistan have national RISC-V processor design initiatives. And I think we're seeing here a desire for sovereign control over technology and to avoid backdoors from other nations that might be in certain pieces of technology. There's also strong interest from chip makers in China. So if you remember back in 2019, US companies were banned from doing business with Huawei. And I think there's concern there of like what company might be next. ARM ultimately was deemed to be a UK origin technology, so they could continue to do business with Huawei, but how long will that last and how will the NVIDIA acquisition impact that? So sometimes I hear the question, is RISC-V an open source processor? So that's not quite right. RISC-V is a set of specifications under an open license, under an open source license. And RISC-V implementations can both be open source and proprietary. So just because it's RISC-V doesn't mean that it's an open source implementation of a processor. It just means it's implementing the open RISC-V specification. And that's important because open specifications make open source implementations possible. An open ISA like RISC-V enables there to be open source processor implementations. So with RISC-V, we can have fully open source chips if the people that are doing the implementations choose to do that. So RISC-V has what's called a privileged architecture, and this is used for running a full operating system like Linux. So there's 3 different privilege modes. There's machine load or M mode where you find the bootloader and firmware. There's supervisor mode or S mode where you find the operating system kernel like Linux. And then finally there's user mode or U mode where you have the applications running. There's also a hypervisor spec that's in draft that also gives a HS, which is a modified S mode. So the RISC-V boot flow is similar to what you might have seen on ARM systems, but there is a piece in the middle there which is called OpenSPI, which you may not be familiar with. Also, before I proceed, just one thing I wanted to point out which confused me for a little while when I was learning RISC-V terminology is you'll see the term HART, and this stands for Hardware Thread of Execution. So you can think of it as a core or a schedulable unit. So I mentioned SBI. So this stands for the Supervisor Binary Interface, and this is something that's specific to RISC-V. So it's the calling convention between the supervisor mode or S mode OS and the supervisor execution environment or SEE that's running in machine mode. And this allows the supervisor mode software to be written so that's portable to all different RISC-V implementations. So this is important so the architectural support in the Linux kernel for RISC-V is not written for a specific RISC-V chip. It's written to the RISC-V architecture, and SBI acts as the abstraction there that makes that possible. And this came out of the Unix class platform spec working group. It's chaired by Elstone, and recently it changed the name to the RISC-V platform spec working group. The idea there was to be broader than just Linux. OpenSBI is an open source implementation of that SBI standard. And the idea here is that it has layers of implementation. So at the core, there's the SBI library that implements SBI. And then there's platform-specific libraries for different RISC-V SoCs. And then there's even complete platform-specific reference firmware for different SoCs and boards. So this provides a runtime in N mode. So typically it's used in the boot stage following the ROM loader, and it provides support for several reference platforms and generic drivers that are included for M mode to be able to operate. And that's the machine mode, the bare metal kind of mode. Something that's been standard for a long time in the Intel world is UEFI, and with the advent of ARM v8 and 64-bit ARM, also saw that starting to be adopted for ARM servers. And UEFI support is there for RISC-V. So support in the Linux kernel is coming in 5.10. There's already implementations for UEFI and RISC-V with U-Boot and Tiano Core EDK2, and Grub2 can be used as a UEFI payload on RISC-V. RISC-V is also well supported in QEMU, so if you don't have any hardware, you can actually run either full 64-bit or 32-bit RISC-V Linux in QEMU. And if you click on that link there, there's a nice tutorial that'll get you going with running RISC-V Linux on your PC or laptop. So RISC-V has been supported in the Linux kernel since the initial port by Palmer back in Linux 4.15. If you're interested in following along, subscribe to the mailing list there, and there's also the archives available on Lore. And a great talk that was given earlier this year was from Bjorn Topol at the Munich RISC-V meetup, one of the virtual meetups that I had mentioned earlier. And it's called What's Missing in RISC-V Linux and How You Can Help. And one of the things that he mentioned in the talk was RISC-V, the RISC-V support in Linux is a great way to learn the nitty-gritty details of the kernel. And it's also a fun, friendly, and still pretty small community, the RISC-V architecture support in comparison to Linux as a whole, which is thousands of developers. And one of the things from his talk that he mentioned was there's this script in the Linux source that you can run, and it shows you all the architecture features that still need work on. So if you're interested in digging in, these are the things that are still necessary to do for the architecture. And some of the recent work for debug and trace and security RISC-V support in the Linux kernel includes the EPPF JIT. So this is important because EPPF is bringing lots of exciting capabilities to Linux, and it's important for that to be supported on RISC-V. Also, K-probes and K-rep probes will enable BPF trace and make perf much more usable, and those are very powerful tools. There's also KGDB and KDB support being worked on, which is useful for debugging. Also kexec and kdump and relocatable kernel work is being done, which will help address space layout randomization implementation. And also the syscaller fuzzing bot, or the syscaller, which does fuzzing to discover security vulnerabilities, now supports RISC-V as well. The recent work on hardware support includes KVM. So KVM is basically complete now. It's just waiting on the ratification of that hypervisor specification. There's also support being worked on for the Vector ISA, which is also a draft extension that has going to be pretty exciting capabilities in terms of doing heavier processing in RISC-V. There's also SV48 support, which is four-level page table for up to 64 terabytes of physical RAM, which should hopefully be enough for a while. And there's also work to unify NUMA implementations for bigger systems. There's also work being done to support some of the more recent RISC-V dev boards. So Linux distros, Fedora has a port which aims to provide the full Fedora experience on RISC-V. And they're at the point now where you can either run Fedora RISC-V under QEMU, like on your desktop or on a server, and it's also supported on one of the RISC-V development boards that's currently available. We'll talk a little bit more about the different dev boards that are out there in a minute. And if you want to, you can go through the installation instructions and start running RISC-V Fedora on your PC using QEMU. There's also a port of Debian to RISC-V, and Debian is known for having the massive source packages of like 20,000. And the good news is over 95% of those packages are building right now for RISC-V, and you can see there on that graph the top gray line is RISC-V. And if you don't need a full general Linux distro, there's also support for RISC-V and Open Embedded and Yocto project through the Meta RISC-V layer. There's also support in Buildroot as well, and if you want to go through, there's a great tutorial from Michael at Bootland of how to build an embedded Linux system from scratch in 40 minutes using Buildroot. So what about actual chips? So we talked about how there's great QEMU support, but we want to actually run on real hardware. So SiFive is a startup founded by some of the people from that Berkeley team. And back in 2018, they debuted the FU540, which was the first RISC-V system on chip that could run Linux. It had 4 64-bit cores that were intended for running Linux, and also a lower power core for doing system management tasks. It has 64-bit DDR4 interface, gigabit Ethernet, kind of the standard peripherals you have. Unfortunately, not USB. And along with that, they announced back in 2018 and came out with the first Linux-capable RISC-V dev board called the SiFive Freedom Unleashed. And this is what you saw back on the Fedora slide. The only other things that's neat is the actual board design for it is open source hardware. So it was quite high performance compared to FPGAs, which is one of the other alternatives. The FU540 SoC is clocked, it's going to be 10 times or more faster than the soft cores. The other thing I wanted to note here was sometimes you'll hear the term ASIC, and that usually is referring to a system on chip that has a hard processor core constructed by silicon fabrication instead of a soft core that's loaded into an FPGA. And with an ASIC, we can run the clock much, much faster than on an FPGA. However, this board was too expensive for widespread adoption. It sold for about $1,000 on crowd supply, and it's not available anymore. And the chip itself was never sold separately. And the reason for this is SiFive's core business is designing cores. It's not to build SoCs or dev boards. But one of the nice things about this is if you get the expansion hardware, including a graphics card, you can actually run a full Fedora GNOME image on RISC-V, which is neat to see. And one of SiFive's customers was Microchip, and they came out recently with the PolarFire SoC. So this is similar to that SiFive U540, but it adds an FPGA. So it had, like the SiFive SoC, it has 4 64-bit cores that can run Linux. It has DDR interface. This one also has PCI Express and USB and gigabit Ethernet. And the great thing about this too is that it's a full commercial product family. So it's going to be available from distributors. And if you're wondering, I didn't realize Microchip made FPGAs. Well, this is because it's formerly Microsemi, which is now part of Microchip. And to debut this SoC, they came out with the PolarFire SoC dev board. This was announced back in July for $500, so half the cost of that SiFive Unleashed board. The pre-orders are now shipping, and it'll be available soon from distributors. And this one has the RISC-V cores clocked at 600 megahertz, and it has the large FPGA fabric with 250,000 logic elements. And it has 2 gigabytes of DDR memory and 8 gigabytes of eMMC flash. So it actually comes with Linux installed on it, which is nice. One of the other boards I wanted to mention that's using that PolarFire SoC is the Savvy board, and one of the neat things here is designed to be able to be stacking, so if you want to build a cluster of these boards. In addition, it has dual 10 gigabit fiber Ethernet, so the idea here, I think, probably for HPC sort of workloads. It also brings out PCI Express over Type-C connectors. But those boards are pretty expensive and might not be in your budget, but you still want to play around with RISC-V. So I recommend checking out the Kendryte K210. It's a 400 megahertz dual core, 64-bit core. It has 8 megabytes of SRAM, which is a lot of SRAM, but it doesn't have DRAM. So it makes it a little bit difficult for us to run Linux. And you can find this in affordable dev boards from SiPede, such as the SiPede Max Bit, which I'm holding here, which is only $13. And at first it didn't seem like it was going to be possible, but last year some hackers like Damien Lamal and Christopher Helvig got it to work and added the support to Linux 5.8. There's also now support in U-boot for 2 of the boards from Sean Anderson. And part of the trick there is the chip does have an MMU, but it's not supported. It's an earlier draft spec and it's not supported in Linux, so they have to treat it as not having an MMU and just running Linux in M mode or machine mode. So the problem there is that the 8 megabytes runs out very quickly. Since we don't have virtual memory, we can't do shared libraries, so we end up running out of memory very quickly. There's a few people working on potentially ways to improve that. So there's a talk there linked that you can check out if you want to find out more about that. But it can run BusyBox, so the kind of the default instructions are you can use build-root to build a rootfs with BusyBox, and that's being in the process of being upstreamed. There's a great tutorial on SiNext software that takes you through all the different steps that you need to go through to build the kernel and build the rootfs and load it up onto the board. Here's me running at what was at the time the mainline Linux on it, and you know, for $13, I highly recommend getting one of these boards and checking it out and building the kernel and building a rootfs and putting it on the board and just kind of getting familiar with some of the different tools. Now, something that's going to be more practical because it has DRAM is the Pico Rio. So this is an open source project from Rio's lab, and the goal here is to create a low-cost Linux-capable RISC-V platform. We were very excited back in September during the RISC-V Global Summit that this was announced. They have 3 different phases that they want to do of the system on chip. The first one of which is expected to start having samples by the end of this year, so that's pretty exciting. SiFive also has followed up back in October with a new version of the dev board. So the new one's called Unmatched, and this one is on crowd supply right now for $665, and it's expected to ship at the beginning of next year. This has a new SoC from SiFive called the FU740, which is a much higher performance one with 4 64-bit cores for running Linux, and also one of those companion cores as well. One of the things you might notice is actually a mini ITX form factor, so it's possible to build a kind of a proper PC out of this, and that's what was demoed at a conference recently. The board has 8 gigabytes of DDR4 memory, it has 4 USB 3 ports, has gigabit Ethernet, it also has a full PCI Express expansion slot, and also has connectors, M2 connectors for things like NVMe SSDs and Wi-Fi and Bluetooth modules. And the highest performance chip that's been announced so far is from T-Head, which is a subsidiary of Alibaba. And this is called the Genty 910. It's a 16-core, or you might also see it referred to as C910. It's a 16-core, 2.5 gigahertz processor. And this implements a draft version of the vector extension, which is quite interesting. And this is expected to debut next year. There's also, SiPeed announced just like 2 weeks ago that they're going to be doing a board with a new all-winner SoC. So this actually is going to be using another core, a smaller core designed by Alibaba T-Head that's going to be in an all-winner system on chip. So it's just going to be a single core up to 1 gigahertz, but the board's going to be less than $13, and they're saying it's going to have at least 256 megabytes of DRAM, so it'll be much more useful for running Linux than that Kendryte board. However, there aren't really that many options when it comes to hardware on Linux with RISC-V. So one of the other alternatives is to leverage FPGAs. So an FPGA is a field programmable gate array. So this is a chip that you can think of as being a sea or an ocean of different logic elements. And these can be configured to be any sort of digital logic that we want them to be. And if we have enough, we can even configure it to be a processor core, which we call a soft core. Now, when I learned FPGAs maybe about 15 years ago, well, we had to use proprietary tools from the FPGA vendor. And one of the awesome things that's happened more recently is there's a strong open FPGA community that's been working on open source toolchains for certain FPGAs. So this started off with the Lattice ICE 40 with a project called Project Ice Storm by Claire Wolf. This is a smaller FPGA, but it paved the way towards more capable FPGAs being supported, such as the Lattice ECP5, which is supported by Project Trellis, and much more capable FPGAs are from Xilinx, and Project X-Ray and SymbolFlow are working on also supporting the Xilinx Series 7, and that should be coming soon. One of the things you can think of these open FPGA toolchains as being kind of similar to GCC for FPGAs. The idea here is we can use free software to take our processor design and turn it into what's called the bit stream to load into the FPGA using only open source software, which is a pretty awesome thing that's happened in the last few years. So I mentioned the ECP5 is supported by the open source FPGA tools. and I wanted to talk about a project I was involved with last year. So as is the fashion now for many hardware hacking conferences, is to have an electronic conference badge that you can put graphics on and play games and have different sorts of interactions. And we were at the Hackaday Supercon last year, and it was in this kind of large Game Boy form factor, and it had a ECP5 FPGA on it. And it was designed to kind of run this graphics engine where people could develop games and put little animations on the color LCD of their name and things like that. But several of us at the conference thought, okay, that's nice, but what about running Linux? So we got together and we called ourselves Team Linux on Badge. And we first tried the 16 megabytes of SPI connected SRAM that was on the board. But that didn't work out. But because it was a hardware hacking conference, one of the people, Jacob Creedon, he had already designed an add-in cartridge that had 32 megabytes of SD RAM, which did prove to be sufficient for running Linux. And the design of the badge was a Game Boy thing, so on the back there was a header to plug in these other circuit boards, which were called cartridges. So here's the 32 megabytes of SD RAM plugged into the badge on the back. And I mentioned softcores earlier, and I thought this was a neat way of kind of conceptualizing it at or visualizing it at a macro level. So this is an FPGA where the gates have been configured to serve as a soft processor core that can run Linux. And you can see that there's actually still space left there for defining other sorts of logic. Also, a great follow, ICO TC on Twitter if you're interested in open FPGA discussions. But specifically, how did we create the SoC that got loaded into that ECP5 FPGA on the Hackaday badge to run Linux? Well, we used Python, which may be a bit surprising, but Python has advantages over traditional hardware description languages like VHDL or Verilog. Many people are already familiar with Python versus HDLs. Like at the conference, most of us came from a software engineering background. And there are currently there's currently more software developers than hardware designers, so a nice way to get more people into doing chip-level hardware design is to leverage a language like Python. Specifically, we used Migen, which is a Python framework that can automate chip design. It leverages the object-oriented modular nature of Python, and it produces Verilog code just like all the other tools, so it can be used with existing chip design workflows. Even though we're coding in Python, it produces Verilog ultimately. There's a great talk about using Python for creating hardware to record open source conferences, so I highly recommend checking that out if you're interested to learn some of the more background behind it. And that's from Tim Ansel, and he was one of the people that was part of Team Badge on Linux at the Hackaday conference. So to give you an example of what Migen looks like, so on the left there in VHDL, which is a traditional hardware description language, this is, I believe, a D flip-flop, which is a simple digital circuit. On the right there, we have the same circuit, same digital logic defined there in Python. And to me, I think the right-hand side actually is easier to understand. So you can see how it's leveraging kind of the object-oriented nature of Python to, I think, make it a little bit more understandable. And then based on Migen, there's a framework called LiteX, which allows us to build a full system on chip that can be loaded into the FPGA. And LiteX has a collection of open cores for things like DRAM and Ethernet and PCI Express and SATA and more. So rather than having to write our own DRAM controller or our own serial controller, we can just grab those open cores from the LiteX project. And one of the things that brought all this together is a repository called Linux on LiteX Vexriscv. So Vexriscv is a 32-bit Linux-capable RISC-V implementation designed to be FPGA friendly, so it makes efficient use of the resources that are on FPGA. And it's written in a hardware description language called Spinal, which is based on Scala, so also an object-oriented language that can kind of leverage software engineering skills. And it builds a system on chip using Vexrisc as the core and the different LiteX modules. So we can pull in the ones we need, like Light DRAM or Light Ethernet or SD card or PCI Express. And while you probably don't have the Hackaday badge, Linux on LiteX Vexriscv actually supports a large number of FPGA dev boards, and there's also a simulator if you don't have a dev board. So you can actually just go and clone that repository and run the build script, and you'll be running Linux on a simulated RISC-V core on your PC. And here is me with the badge connected to the serial port or the terminal emulator on my laptop, so we can see the console on the badge. And you can see there that what's happened here is we've used the open source tools to synthesize the LiteX design into a bit stream that gets loaded onto the ECP5 FPGA. And then once the soft core is running inside the FPGA, we then load the Linux kernel up onto it in a rootfs, and it boots into the Linux kernel and loads up BusyBox there, which you can see in the window. So when the conference ended, thought it was a good idea to upstream the work that we had done to get it running on the badge. And while most people probably don't have the badge unless you're one of the couple hundred people at the conference, this is a good example of how to add a new board to Linux on LiteX Vexriscv. And to give you an idea of what the Python Migen syntax looks like, this is what's called the pin constraints for the project, and this is how it maps the pins on the FPGA to the different signals inside the design. Another good example of the extensibility of LiteX and Migen is we had a DRAM chip on that cartridge that was not already supported in LiteDRAM, so we had to add that in. However, it just involved inheriting or extending the SDRAM module to have a new class specific to our DRAM chip, so we just had to go and grab the different timings from the datasheet and plug them in there. So much simpler than having to write our own DRAM controller. We just leveraged the object-oriented nature of Python to extend it with just the specifics to our hardware that was new. Another interesting thing that happened in this project was, so we got it working, but it was booting really slow. It was taking almost 5 minutes. So I posted a GitHub issue, and LiteX is maintained by a user named Enjoy Digital, who his actual name is Florent. Really nice guy and really responsive maintainer. So within a few hours, he had actually posted a patch that improved the performance by 10 times. So it was booting up in less than 30 seconds, which was pretty awesome to see. And also, just to give you more of that Python flavor of what Migen looks like, you can see here this is the diff of part of the changes that he made to optimize Linux running on our badge. You know, because we had slow, I think just 8-bit SDRAM, memory accesses were pretty expensive. So in this case, the L2 cache data width was made larger. And this allowed us to have better performance. And you can see here in this diff, to me it's a little bit more understandable because it's in Python versus something like Verilog or VHDL. And you might have noticed there was an LCD. Well, Greg Davil is an awesome hardware hacker in Australia, and a few weeks after the conference, he was actually able to get the LCD working with the Lite video module. So now we don't have to have it connected to a PC to see Linux boot up on it and get to the BusyBox shell. So while you probably don't have the Hackaday badge and it's not available for sale, but there are other open source boards that have the ECP5 FPGA, one of which is from a hackerspace in Croatia called Radiona. It's the ULX3S. It also has the 32 megabytes of SD-RAM, so we can run Linux on it, and it's sold on Crowd Supply and Mauser. And then another board I like a lot from Greg is the Orange Crab. It has 120 megabytes of DDR memory, so it's much more capable of running Linux. It has more space and a faster memory interface. And it's in this neat little form factor called Feather, which you might have seen different Adafruit boards having. And you can get that on GroupGets. And you know, if you're new to FPGA, starting with a larger FPGA like the ECP5 with a soft core running Linux is probably not the best place to start. So I highly recommend checking out the FOMU. It's an open source board, and there's a great online workshop that goes along with it. It's a tiny little board. It fits inside the USB port, so you can take it around in your laptop everywhere. And it has a great tutorial that takes you through the process of blinking LED, first in MicroPython, and then in Verilog, and then finally in Migen in LiteX. If you don't have any hardware at all, highly recommend Renode. It's an open source project started by Ant Micro, and it can simulate physical hardware systems, including CPUs and peripherals and sensors, and even wired or wireless nodes network, a wired or wireless network with different nodes. And one of the great things about Renode is it has profile for different dev boards. So remember I mentioned that SiFive Unmatched board, that the Fedora project and other people were using. Well, it's expensive and hard to find. So that's, if you don't have the board, you can still run the software that's supposed to run on it by using the profile in Renode. So here's an example of my laptop pretending to be the SiFive Unmatched board, booting up the same software that runs on the board. And because it's a full modern laptop, it actually runs pretty fast, so it doesn't feel like it's some super slow simulator. Finally, to leave you with, I thought this was a really interesting concept that I came across, the idea of a trustworthy self-hosted computer. So Gabriel Samlo at Carnegie Mellon came up with this concept of, okay, now we have open source tools that we can use to load designs into an FPGA, and we have soft cores that can run inside of the FPGA that are capable of running Linux. And we can run those FPGA tools inside of Linux. So we can actually create a self-hosted system that can build itself, which is, I think, quite an interesting concept. Highly recommend checking out the talk that he has that I linked to. And here's just one of the slides from it showing how he's using LiteX along with Rocket, which is a core from Berkeley, and how those all come together to be a self-hosted FPGA Linux computer. So thank you for watching, and I'm happy to take any questions online, and hopefully we'll be chatting throughout the rest of the conference, and I think the Slack that we'll have for the different talks and topics. Thank you.